Lecture 32 of our series on numerical methods in civil engineering, we will talk about orthogonal polynomials. Before we do that, let me recapitulate what we talked about in our last class, and particularly what we talked about at the end of the last class, when we were talking about the relative merits of polynomial versus linear interpolation. We looked at polynomial interpolation and we suggested that an alternative way, instead if we have a grid with m plus 1 points, instead of trying to fit an mth order polynomial through these points, an alternative approach might be to use linear interpolation. Suppose we know the function values at x0 through xm and we are interested in evaluating the function at any point x, where x lies between any two grid points xk minus 1 and xk. Then instead of going through the expense of fitting an mth order polynomial through the points x0 through xm, a simpler solution may be to calculate f of x by linearly interpolating between f of xk and f of xk minus 1, which are basically the function values evaluated at xk and xk minus 1. We can always do that, but we have to find out there are two things we have to consider. First is how accurate is our linear interpolation, number one, that should be the main one of the main considerations. The other consideration should be how expensive, how computationally expensive or how computationally inexpensive it is compared to using a polynomial interpolation, right. So, when first we want to consider the question of accuracy, when is linear interpolation sufficiently accurate? Suppose we have a table of equidistant correctly rounded function values, meaning that we have rounded them correctly, right, so that we know that they are accurate up to t decimal places, right. So, that we know that those function values are accurate up to t decimal places. Last time I talked about a particular result which states that if given a table of equidistant correctly rounded function values, if we are assured that the second difference calculated from the function values satisfies this condition, that is the second difference is very small, right, and it is as small as 4 into 10 to the power minus t, right, where t is the denotes the last digit in the function values, right, then the total error in linear interpolation can only slightly exceed 10 to the power minus t in magnitude. But when is this condition going to be satisfied? When is the second difference going to be so small that it is lesser than or equal to 4 into 10 to the power minus t? When my function values are varying relatively slowly, right, when my curve, when the difference between the function values is not large, right. Only in that case, when I take the second difference is going to be really small, right. So, the assumption, inbuilt assumption here is that the function values are not varying very much, right, in that interval, right. Only then is my linear interpolation going to give me accurate results, accurate up to this level, right. The total error in linear interpolation can only slightly exceed 10 to the power minus t in magnitude. And what do we mean by the total interpolation error, which I also talked about last time? The total interpolation error has basically got three components. It is the round off error due to uncertainty in the known function values, right, there is some round off there. Then there is a truncation error, basically you are using an interpolant of a certain order, a polynomial of a certain order. Inbuilt into that is the assumption that there is an error term, there is a remainder term which contributes to the error. So, that is the truncation error, and finally, there is the round off error made during the computations, during the actual calculations you do to find out your interpolated value. So, the above bound on the error due to linear interpolation assumes that while RT and Rx are non-zero, Rc are sufficiently small to be ignored. So, we are just considering Rx and Rt when we talk about this bound. However, for this condition to be satisfied, the points x0, x1 through xm must be sufficiently closely spaced. Initially I told you that the function values should not vary that much, right, in that interval. That is equivalent to saying that my interval is very small, that my points are closely spaced, right. So, given a fixed interval, this requires the knowledge of function values in a narrowly spaced grid. Thus, for linear interpolation to give accurate results, many more table values are needed, because our grid we have to have very narrowly spaced grid, right, function values at many points, so that the function is varying slowly, right, and that means if I have a large interval, that means I have many function values that need to be evaluated, right. So, I have my grid has many points. As an example, suppose an interpolant has to be found for the function natural log of x over the interval x greater than or equal to 1, less than or equal to 5. So, we know this function value, right, we know this function, and we know that, and we can calculate the function values at points in a grid, right, and then we try to fit a polynomial to these function values, right. It turns out if we try to do it with linear interpolation, we try to fit lines between the function values, right, and then try to interpolate the value at an unknown point from my interpolant, right. In that case, if I use a linear interpolation, I will need 450 function values, right, while if I just use a quadratic interpolation, I will need 100 function values in order to get the same level of accuracy. So, we have talked about Newton's interpolation formula. Basically, let us recall, Newton's interpolation formula is a way to figure out the polynomials, to calculate the coefficients of the polynomials of the polynomial which we are using to interpolate, right. Instead, there is one brute force way, which I told you right in the beginning, where you actually go ahead and invert the matrix to find the coefficients of the polynomials, right. But instead of that, we talked about the Newton's interpolation formula, which allows you to calculate the coefficients of your polynomial, of your interpolant, relatively easily. There are other interpolation formulas, for instance the Lagrange interpolation formula, which is particularly popular in the context of finite element methods, right. In addition to Newton's interpolation, we are going to talk about that, and the Lagrange interpolation formula goes like this. It says that my interpolation formula is given by this sort of a function. Fi are the known function values, right, known function values at the grid points, and delta I x is basically the interpolant. Lagrangian polynomials are widely used in the finite element method to construct shape functions at the nodes of the finite element mesh. Delta I is the polynomial of degree m and satisfies the relation delta I xj is equal to 1. So, delta I for each of these polynomials are associated with a grid point, right, and that polynomial assumes the value 1 at the grid point and is 0 everywhere else, right, and my total interpolant is obtained by summing those polynomials, scaling each polynomial by the function value at its grid point, at the grid point at which the polynomial is 1, right, scaling that polynomial with that function value and summing it together, right. So, delta I x j is equal to 1 if j is equal to I, right, and is equal to 0 everywhere, right, else, right, at all. When I say everywhere else, I mean at all the other grid points. Hence, delta I x must have this following form, right. In order to satisfy that condition, delta I x must have the following form: x minus x j is pi denotes the product, x minus x j divided by x I minus x j. On the top, for delta I x, we have everything. If you look at the second term in each of these first brackets, there is x 0, x 1, x I minus 1, but there is a missing x I, right. the bottom I have xi minus x0, xi minus x1 through xi plus 1, right. Actually it should need not stop at xi plus 1, it can go up to m, right. It can go up to m. I have missed, I have not included the higher terms, right. So this gives me something like that, right. So given this form of delta I x, by definition if I define q x like this, if I define q x like this, q x j will be equal to f of j, right. So that is your Lagrange interpolation formula. Again it's the same thing. I know the function values at certain grid points, it's a question of fitting a polynomial to those function values, right. Another commonly used interpolation formula, which is also a solution of the general interpolation problem, is Hermite interpolation. The advantage of Hermite interpolation is that we can, using Hermite interpolation, we can interpolate not only the function values but also the derivatives of the function values, right. You can interpolate the derivatives of the function values. This involves using Newton interpolation formula to fit not only the function values but also one or more known derivatives of the interpolation points. So if we know not only the function values at the interpolation points but we also know the derivatives, then we can use Hermite interpolation, and as we will see, Hermite interpolation is really a special case of Newton's interpolation. Thus one can generate a polynomial fit to the derivatives of a function rather than to the function itself. From Newton's interpolation formula, we recall that the coefficients are defined in terms of the divided difference operator. Went through a lot of pain to show that for Newton's interpolation you can find the coefficients by evaluating this divided difference operator, and we showed how to evaluate those divided difference operators, right. And in particular if you want to evaluate C1, right, the coefficient of the term linear in x, then that can be obtained like this: f of x0 x1, which is basically the first order divided difference operator, which is given by f of x1 minus f of x0 x1 minus x0. Now take the limit of this. If we take the limit of this as x1 tends to x0, what do we get here? We get f of x1 minus f of x0 divided by x1 minus x0, the limit x1 tends to x0, that is equal to the derivative of the function at x0. So what does that tell me? That tells me in the limit that x1 becomes very close to x0, right, in that case my first coefficient I can get that by equating that to the derivative, to the known derivative value at x0, right, to the known derivative value at x0. Similarly I can do that with higher order derivatives as well. So higher order derivative, if I know higher order derivative values at interpolation points, I can also use them to define the coefficients. How do we do that? Well, let us recall that Ck is equal to this for k less than or equal to m. We also recall that we showed this: f of x0 x1 xk minus 1 x is equal to the kth derivative of f evaluated at xi divided by factorial k, where xi belongs to the interval which includes basically xi belongs to the smallest interval which includes the points x0 x1 xk and x, right. So if we consider this equation and we set the limit x1 tends to x0 x2, all the grid points, the grid becomes smaller and smaller. So I am interested in taking the derivative, right. So these things x1 tends to x0, x2 tends to x0 through xk minus 1 x0, we get Ck is equal to the kth derivative of f evaluated at x0 divided by factorial k. So I can get the Ckth term in my polynomial expansion using Hermite interpolation by this value, right, this value, right. So why does I becomes x0? Because everything basically collapses to x0. So, my interval becomes smaller and smaller, and so I get f of k x 0, right. So, that is how we can use Hermite interpolation to fit a polynomial to not only the function values, but also the derivatives. This, for those of you who have a structural mechanics background, this is used for Bernoulli-Euler beams, right. For Bernoulli-Euler beams, when we want to interpolate the slopes, when particularly in a finite element context, when we are trying to solve a Bernoulli-Euler beam, we need to interpolate not only the displacements at the grid points or the nodes, right. We also need to interpolate the slopes at the grid points, right. So, in that case we need to fit that interpolant to not only the function, the displacements, that is the function values at the grid points, but also the derivatives of the function values at the grid points, which are my slopes. Orthogonal polynomials. Another important class of polynomials that are often used in interpolation and possesses many desirable properties are orthogonal polynomials and Chebyshev polynomials. The Chebyshev spelling, you can find it different spelling in different books, right. Some books spell with TCHEBESHAV, I have used the spelling Chebyshev, but they are probably the most important examples of a triangle family of orthogonal polynomials. Now, these Chebyshev polynomials are just a particular instance of something which is much more broader and much more general, that is the family of general theory of orthogonal polynomials. They are a particular type of orthogonal polynomials. We will talk about the general theory not in great detail, but at least the basic features of the general theory some point later on in this lecture. But first I want to motivate the lecture by talking about one particular type of orthogonal polynomials, these Chebyshev polynomials. These are very important because they possess some very desirable properties, as we will see later on. How do we construct Chebyshev polynomials? Well, Chebyshev polynomials are constructed using the cosine function and taking advantage of the fact that I can write cos of n phi for any n greater than 1 as a polynomial in cos of phi, right. I can write cos of n phi as a polynomial in cos of phi. Let us see an example. Well, how can we do, why can we do this? Well, it is just because of this particular formula, right. I can always write cos of n plus 1 phi plus cos of n minus 1 phi as 2 cosine of phi and times cos of n phi, right. So, for n is equal to 1, I can write using this formula right here. I can write cosine, so n is equal to 1, cosine of 2 phi is equal to 2 cos square phi minus 1. This part becomes 1, right, 1 minus 1 0. So, they pull it to the left, I get cos of 2 phi is equal to 2 cos square phi minus 1. For n is equal to 2, I have cos of 3 phi plus cos of 2 phi is equal to 2 cos of phi times cos of 2 phi. So, I know cos of 2 phi in terms of cos of phi, right. So, I have cos of 2 phi here, I know in terms of cos of phi. So, I can write cos of 3 phi entirely in terms of cos of phi, right. So, cos of 3 phi is equal to 2 cos of phi times cos of 2 phi minus cos of 2 phi, right. I know cos of 2 phi in terms of cos of phi. So, I can write cos of 3 phi entirely in terms of cos of phi. Similarly, I can write cos of 4 phi entirely in terms of cos of phi, and similarly for higher order terms as well. Any integer n, cos of n phi, I can always represent that in terms of cosine of phi, right. And then I set x is equal to cosine of phi, or phi is equal to cosine inverse of x to get the Chebyshev polynomials in the interval x, it must be less than or equal to minus 1, greater than or equal to minus 1, less than or equal to 1. Why does x have to satisfy this bound? Well, because I am setting x is equal to cosine of phi, right. and n can be equal to 0, can be any value as we just talked about. So then we define the Chebyshev polynomial of order n with argument x as cosine of n phi, which is equal to cosine of n times cos inverse of x, right. Thus T0 of x is nothing but cosine of 0, which must be equal to 1. T1 of x is equal to cos of n times cosine inverse of x, right, which is equal to x, right. T2 of x is equal to T2 of x is going to be 2 cos square phi minus 1, which is equal to 2x square minus 1, right, 2x square minus 1. T3 of x is equal to 4 cos cube phi minus 3 cos phi, so that is equal to 4x cube minus x, right. So these are my Chebyshev polynomials. So I can generate the nth Chebyshev polynomial, keeping in mind that x is equal to cosine of phi, x is equal to cosine of phi. Is that clear? So T3 of x is cosine of 3 times phi, right, cosine of 3 times phi, which is cos of 3 phi, which is equal to 8 cos of 4 phi minus 8 cos square phi plus 1, which is equal to 8x to the power 4 minus 8x square plus 1, right. So that's how I can generate my Chebyshev polynomials. The Chebyshev polynomials have many useful properties that are common to orthogonal polynomials. For instance, they can be generated recursively. Later on I am going to talk about the recursive formula, the general recursive formula for orthogonal polynomials. What does the general recursive formula do? Well, it tells you that if you know the first few terms of that series, right, of that series of orthogonal polynomials, you can generate higher order terms using that recursive formula, right. So like for instance, for the Chebyshev polynomials, we know that T0x is equal to 1, T1x is equal to x times T0x, because T0x is 1, so x times T0x, and any higher order term in higher order Chebyshev polynomial we can generate by multiplying the next term, the next lower order term, by 2x and subtracting the previous one. 2x times tnx minus tn minus 1x is going to give me tn plus 1x. You can try it out here, right. So if I want to evaluate T3x, instead of doing this, right, instead of doing the substitution here, instead of writing out the expression for cos of 3 phi, right, I can use this recursive relationship. So I am going to take 2x times t 2x minus t 1x, right, that is going to give me T3x. So that is the higher order terms, higher order Chebyshev polynomials can be generated relatively easily without having to evaluate the higher order, the cosine terms, right, cosine terms for high integer values n. So as can be seen from this, as we can see from here, the leading coefficient of each Chebyshev polynomial is 2 to the power n minus 1. So let us take a look. So for the third Chebyshev polynomial, the leading order term is x cube, right, and what is the coefficient of x cube? Is 2 to the power 3 minus 1, 2 to the power 3 minus 1, 2 to the power 2, that is 4. For T2x, what is the leading order term? X square. What is the coefficient of that? It is 2 to the power 2 minus 1 to the power 1, that is 2, right. So the leading order term in each Chebyshev polynomial has coefficient 2 to the power n minus 1. Chebyshev polynomials also satisfy the symmetry property. So what is the symmetry property? It says that Tn of minus x is equal to minus 1 to the power n Tn of x, right. They satisfy the symmetry property. and each Chebyshev polynomial of order n has n zeros in the interval -1 to 1, and the zeros are given by the following. We know Tn of xk is equal to cosine of n phi to the power k, and this has to be equal to 0. Where the Chebyshev polynomial is 0, this has got to be equal to 0. So, when is this equal to 0? This is equal to 0 when n phi k is a multiple of pi by 2, right, is an odd multiple of pi by 2, right. So, n phi k must be equal to 2k plus 1 times pi by 2 for cos of n phi k to be equal to 0, that is for the Chebyshev polynomial to have a 0, right. So, that gives me phi k, the value of phi k. So, these are the values of phi k for which the Chebyshev polynomial is 0. So, I know phi k is equal to this. So, that means x k, which is cos of phi k, is given by this, right. So, these are the points, these are the grid points where my Chebyshev polynomial is going to be 0, right. So, these are the zeros of the Chebyshev polynomial. It turns out that Chebyshev polynomial also have n zeros. The Chebyshev polynomial of order n has n zeros in the interval -1 to 1. It also has n plus 1 extrema in -1 to 1, extrema meaning minimum or maximum, right. This is because the Chebyshev polynomial Tn xk is equal to cosine of n phi k, and I know that mod of cosine of n phi k must be between -1 and 1, right, and it is equal to -1 since it is -1 at pi, it is equal to 1 at 2 pi, right, it is 1 at 2 pi. So, it has got maxima at n phi k at where n phi k is equal to k pi, k equal to 0, 1, 2 through n. Hence, the maxima occur at phi k is equal to k pi by n. So, again we can get the location of the maxima in terms of x using the relation that x k is equal to cos of n phi k. So, the extrema, sorry, not the maxima, the extrema of the Chebyshev polynomial occur at cos of k pi by n, right. So, we have talked about the zeros of the Chebyshev polynomial, we have talked about the extrema of the Chebyshev polynomial. We shall see that these location of these zeros, the location of these extrema are extremely important, right, they are very valuable. The Chebyshev polynomials, I said, are orthogonal polynomials, but they are orthogonal with respect to a certain weighting function, right. So, if I integrate two Chebyshev polynomials of different orders and multiply them with this weighting function 1 minus x square to the power minus half and integrate them within the limit -1 and 1, I am going to get 0 always, so long as I is not equal to j. So, they are orthogonal. They are orthogonal, but they are orthogonal with respect to a certain weighting function, right. If I just take integral within -1 to 1 of T I x T j x, then I am not going to get orthogonality. They are orthogonal only with respect to this weighting function. But if I is equal to j, then this integral is equal to pi if both are equal to 0, and if both are not equal to 0 but both are equal, then I get pi by 2. Well, you can prove that, but it is relatively trivial, so I will just spend a few minutes. So, let x is equal to cos phi, then I am interested in evaluating T I x T j x 1 minus x square to the power minus half. Then I get, recalling that I can write the Chebyshev polynomial in terms of cos phi. So, I get integral between 0 to pi cos of I phi cos of j phi d phi. This term actually disappears because 1 minus x square 1 minus cos square phi half gives me sin phi dx gives me d phi, right. So, that term disappears. So, I have integral of this, that if I evaluate that, if I write it out, right. So, this is equal to cos of I plus j phi plus cos of I minus j phi. If I integrate this between 0 to pi, I will find I get that previous result, right. So, that is for the Chebyshev polynomial in the continuous case, right, where I am trying to integrate it over the interval -1 to 1. So, its assumption is that the function is continuous in that interval. But suppose I do not know the function values at all the points in that interval -1 to 1, I only know it at certain grid points, right. Then I can evaluate this, I can impose this orthogonality condition at the grid points, right. The orthogonality condition is satisfied at the grid points. So, if we consider the discrete case, that is, we evaluate the Chebyshev polynomials at discrete points, then the orthogonality property is satisfied in the following manner. I think I have made a mistake here because I have omitted the weighting function, right. So, sigma k equal to 0 to m Ti x k Tj x k times the weighting function evaluated at that point is equal to 0 if I is not equal to j, is equal to half m plus 1 if I is equal to j is not equal to 0, is equal to m plus 1 if I is equal to j is equal to 0, where the xk's, we note where the xk's are the m plus 1 zeros of the Chebyshev polynomial of order m plus 1. Let us go back and take a look. The sum is from k is equal to 0 to m, and I am evaluating the Chebyshev, I am taking the product of the Chebyshev polynomials of order I and j, but I am evaluating each of them when I am imposing the orthogonality constraint is satisfied at xk, where xk are the zeros of the zeros of the mth order Chebyshev polynomial, right. They are the zeros of the mth order Chebyshev polynomial. Is that clear? Or rather the m plus 1th order Chebyshev polynomial. Is that clear? So, the m plus 1th order Chebyshev polynomial is going to have m plus 1 zeros. There are actually m plus 1 zeros if you go back and take a look. It's from k is equal to 0 to m, right. So, it is not m, it is actually there are m plus 1 zeros, right. So, we need the zeros of the m plus 1th order Chebyshev polynomial, right. The mth order Chebyshev polynomial is only going to have m zeros, right. Another very important property of Chebyshev polynomials, this is probably the most important property of Chebyshev polynomials and why it is so valuable, is among all the polynomials of order n, where n stretches from 0 to infinity, which have leading coefficient 1. So, it can be any order polynomial of any x to the power 15, x to the power 20, it can be any order polynomial. Only criteria, only requirement is that the leading order term in that polynomial has coefficient of 1, right. For all those polynomials, 2 to the power 1 minus n Tn, that is a Chebyshev polynomial of the same order scaled by 2 to the power 1 minus n, is always going to give me the smallest maximum norm in the interval -1 to 1. The Chebyshev polynomial Tm, we saw that its leading order term, so if was something, right. So, if I scale the Chebyshev polynomial with 2 into the 1 to the power minus n, my leading order term in the Chebyshev polynomial is also going to be 1, right, is also going to be 1, right, because we saw, what did we see? We saw that the Chebyshev polynomial, leading coefficient of each Chebyshev polynomial is 2n to the power minus 1. So, if I scale each Chebyshev polynomial by this factor 2 1 to the power minus n, then the leading coefficient is always going to be equal to 1, right. So, so I have a set, suppose I have n is equal to 20, right. So, and I have the Chebyshev polynomial of T20, right, Chebyshev polynomial of order 20 T20, and I scale the Chebyshev polynomial with all the terms in the Chebyshev polynomial by 2 1 minus 20. So, 2 to the power minus 19, right. So, the first order in my the leading coefficient is going to have the term the coefficient 1, it is going to have a coefficient 1. Now that polynomial which I get after scaling the Chebyshev polynomial by 2 to the power 1 minus m, that polynomial is going to have the smallest norm in the maximum norm in the interval -1 to 1 among all polynomials of order 20, provided they have leading the coefficient of the leading order term is 1, right. So, it is guaranteed that it is going to have the smallest norm, right. So, by dividing each term of any polynomial of order n, we can ensure that the leading order term in the polynomial has coefficient 1. Thus, 2 to the power 1 minus n t n has the lowest maximum norm. When I say maximum norm, I mean norm in the the norm the infinity norm, right. I mean the infinity norm for the entire set of polynomials of order n suitably scaled. So, let us look at it again. By dividing each term of any polynomial of order n, we can ensure that the leading order term in the polynomial has coefficient 1. Thus, 2 to the power 1 minus n t n has the lowest maximum norm in -1 1 for the entire set of polynomials of order n suitably scaled, right. Suitably scaled means it is divided by the coefficient of its leading order term, right. And we are going to show this, but this is very important and is very useful. A proof for this can be given in the following manner. Let us suppose that there exists a polynomial Pn of x, right, with leading coefficient 1 such that mod of Pn of x is less than 2 to the power 1 minus n for all x belonging to that interval -1 1. So, suppose we have a polynomial Pn of x whose leading coefficient with highest order term has coefficient 1, right, and we have evaluated Pn of x at every point x in the interval -1 to 1, and we have seen that the magnitude of the polynomial at each after evaluation at each of those points is always less than 2 to the power 1 minus m. So, we have evaluated that polynomial at all points x belonging to -1 1, and we have found that the magnitude of the polynomial is less than 2 to the power 1 minus 1. That is our supposition. Recall that Tn of x has n plus 1 extrema, that is maximum or minimum values. We know that, we have just seen that, right, and the location of those extrema, of those maximum and minimum values, is given by xk is equal to cos of k pi by n, k is equal to 0 1 to through n in the interval -1 1. So, at these points Tn of x k is equal to -1 to the power k, right. Tn of x, so the extrema, right, and recall that is given the Chebyshev polynomials are basically cosines, right. So, the maximum minimum has to be either -1 and 1 or 1, right, and at these points, at these extrema points, Tn of x k is equal to -1 to the power k, k is equal to 0 through n. Hence, we can write Pn of x is less than 2 to the power 1 minus n times Tn of x 0. Why? We know that Pn of x, the magnitude of Pn of x is less than 2 to the power 1 minus m, right, and at k is equal to 0, we know Tn of x 0 is equal to 1, right. So, in that case Pn of x 0 must be less than 2 to the power 1 minus n, right. Its absolute value is less than 2 to the power 1 minus n. So, if I remove the absolute value sign, I know that this is positive. So, Pn of x 0 must be less than 2 to the power 1 minus n times Tn of x 0. What about x 1? At x 1, Tn of x 1 is going to be negative, right. X 1 is the 0 corresponding to k is equal to 1, right. At this point -1 to the power k, so I know that that is negative. So, I am guaranteed that Pn evaluated at x 1 must be greater than 2 to the power 1 minus n times this is negative, right. And if I know that the this is bounded, this norm of this is less than 2 to the power 1 minus n. So, Pn of x1 must be, this is the lower bound, right, that is the upper bound, that is the lower bound. So, Pn of x1 must be greater than this value. Similarly, Pn of x2 must be less than this value, because this becomes positive then, right. So, Pn of x2 must be less than 2 to the power 1 minus n times this. So, what do we see? We see that Pn of x0 is basically alternating in sign, right. Hence, the polynomial Pn of x minus 2 to the power 1 minus n Tn x must change sign in each interval. Let us go back and take a look again. So, Pn of x is less than this, right, Pn of x is greater than that. So, Pn of x2 is less than that. So, if I construct a second polynomial, right, basically Pn of x minus 2 to the power 1 minus n times Tn of x, that polynomial is going to be alternating in sign. So, here it is going to be negative, here it is going to be positive, here it is going to be negative again, right. So, it basically alternates in sign. Hence, the polynomial Pnx minus 2 to the power 1 minus n Tnx must change sign in each interval xk plus 1, k is equal to 0 through 1 through n minus 1 between the zeros of tk. So, if I draw, if I on the x axis I mark out the zeros of my polynomial, right, of my polynomial Tn, right. If I mark out the zeros, and then if I evaluate this function, then I will find that this function is always changing sign between the zeros, right. Between this, it is changing sign, it is becoming positive, it is becoming negative, right. So, in those intervals, right. Since there are n such intervals in minus 1 to 1, right, since there are n such intervals in minus 1 to 1, this means this function must have n zeros in the interval, right. It is changing sign in each interval, it is changing sign between these zeros, right, it is changing sign. That means between these two zeros it has a 0, right. Between the zeros of the Chebyshev polynomial, this polynomial has a 0. Between any two zeros of the Chebyshev polynomial, this polynomial has a 0, right. And since there are n intervals between the zeros of the Chebyshev polynomial, right, that means there are n zeros of this polynomial, right. This polynomial has got n zeros. There are n plus 1 extremes, right, the n plus 1 extremes, right. So, between those two there are, it is having a 0. So, there must be n zeros, right, n zeros, right. I hope I made myself clear, right. So, there are n zeros, but let us look at this polynomial again, Pn of x minus 2 to the power 1 minus n Tn of x. We know that the leading order term of 2 to the power 1 minus n Tn of x is 1, right, because we have divided by 2 to the power 1 minus n. The leading order term of Pn of x is also 1, that is what we assumed. Pn of x is a polynomial with leading coefficient 1. So, what does that mean? That means that the leading order terms, they cancel each other out. So, that means that this polynomial Pn of x minus 2 to the power 1 minus Tn of x is not really a polynomial of order n, it is a polynomial of order n minus 1, because it has cancelled out the leading order term. Since it is a polynomial of order n minus 1, it can have at most n minus 1 roots, right. A polynomial of n minus 1, a quadratic equation has 2 roots, cubic equation has 3 roots, right. Polynomial of order n minus 1 can at most have n minus 1 roots, it can't have n roots, right. Hence a polynomial, so that means such a polynomial cannot exist. hence a polynomial Pnx with leading coefficient 1 such that mod of Pn of x is less than 2 to the power 1 minus 1 in for any x belonging to this interval cannot exist, because that was what we assumed, and if we assume that, we got a conclusion which is patently cannot be true, which is absurd, right. So that means such a polynomial cannot exist, right. So that means, what does that mean? But mod of 2 to the power 1 minus 1 minus n Tn of x is always less than 2 to the power 1 minus n. Why? Because I know that mod of Tn of x is, Tn of x has got extrema 1, right. So mod of 2 to the power 1 minus 2 to the power 1 minus n times Tn of x must always be less than 2 to the power 1 minus x. But we know that there can be no polynomial with leading coefficient 1 such that this is less than 2 to the power 1 minus n. But in case of this polynomial, we know that this is always less than 2 to the power 1 minus n. That means this is the minimum, right. No other polynomial satisfies this condition. No other polynomial there exists with leading coefficient 1 which satisfies this condition that its mod is less than 2 to the power 1 minus n, right. But I know that the Chebyshev polynomial scaled with this quantity satisfies that condition, which shows that this polynomial 2 to the power 1 minus n Tn of x has the smallest maximum norm in the interval minus 1 to n, which is very, very important, right. This is the smallest, it has got the smallest maximum norm in the interval minus 1 to 1. It has got very, very important implications for error, for finding out for optimum location of the grid points to minimize error, right. We shall see that. So this helps us to determine the optimum grid points. This property of the Chebyshev polynomials is extremely useful in determining the optimum location of the grid points. Up till now we have considered equidistant grid points, right, but it turns out, if I looked at an example a couple of lectures back, right, where we were trying to interpolate we were trying to find a fit a polynomial to the function 1 by 1 plus x square, I think that was the function, and we were using a 10th order polynomial, and even then we found that there were very large mismatches near the boundary if we used a equidistant grid, right. I do not know if you remember that, but we saw that. So oftentimes that if we use the equidistant grid, the errors, especially for higher order polynomials and especially at the ends of the interval, become very large, right. Therefore that is why people want to find what should be the optimum location of the grid points in order to minimize the error. How should I locate my grid points so that my interpolant, the error I get from my interpolant, is the minimum possible error, right, and that is where Chebyshev polynomials play a very important role. Suppose we wish to locate the grid points optimally in the interval AB, the interval of interest, where we are trying to do a polynomial interpolation. If the independent variable is x, one can always transform the interval AB to minus 1 to 1 by performing a simple substitution like that, right. If writing x in terms of t, right, I can transform this interval AB to minus 1 to 1. So it does not matter if by the interval that I am doing, I am interested is not minus 1 to 1, I can always do a transformation in variables and convert that interval to minus 1 to 1. In this term, the remainder term in the interpolation designed to fit the values of the function f at the points xi I is equal to 0, 1 through m is given by this. This we have seen earlier, right. The remainder term is given by this t minus t0, t minus t1, fm plus 1 xi m factorial m plus 1, where t0, t1, tm are the grid points. This we have seen earlier, we have proved earlier, right. So this is known, and we recall that xi belongs to xi, this function, this value xi here, this value xi belongs to the interval which is the smallest interval which contains all the roots as well as x, which includes t0, t1, through Tm as well as T, right, in this case T not x. Therefore, xi depends on T, here xi depends on T, right, because xi belongs to the interval, xi belongs to this interval. So, there is a dependence on xi on T, right, but assuming Fm plus xi to be bounded, right, that we can give a maximum value to Fm plus 1 xi in the interval of interest, right, we can write the remainder term as a polynomial, where b by b I am representing an upper bound to the maximum value of this quantity, right. So, we can write the remainder term as a polynomial like this: y is equal to b times t minus t0, t minus t1, t minus t2 through t minus tm, right. Thus, it is clear that this remainder term has zeros at t0, t1, t2, tm, that is, it has got m plus 1 zeros. Remainder has got m plus 1 zeros. Since the remainder is a polynomial of order m plus 1, the zeros of the remainder, that is the error, are therefore about the same as the first neglected term of the expression, right. So, if I did not curtail it at m, right, if I did not curtail it at m, the next higher order term, it would have had m plus 1, right, it would have had m plus 1 zeros, it would have been a higher order polynomial, it would have had m plus 1 zeros, and those zeros are relatively close to the zeros of the remainder, right. Is that clear? But okay, so you bear with me, assume that that is true. But what I want to, I will come back to this in the next class, but before I end this lecture, I want to talk about why the Chebyshev polynomial is important. So, we know that this is my remainder term, right, and I know that the Chebyshev polynomial, the zeros of the Chebyshev polynomial give me the smallest, have the smallest maximum norm. The Chebyshev polynomial has the smallest maximum norm in the interval minus 1 to 1. So, if I locate my grid points t0, t1, t2, tm to coincide with the zeros of the m, is that clear, of the m plus 1th order Chebyshev polynomial, then in that case this remainder term I am guaranteed that the remainder term has the smallest possible error in the interval minus 1 to 1, right. That is why Chebyshev polynomials are very important, right. That is why their zeros are very important, right, because I know that the remainder term is given by this, right, and these are coinciding with my grid points, t0, t1 through tm are coinciding with the grid points. Now, if I make sure that my grid points coincide with the zeros of the Chebyshev polynomial, then I am guaranteed that this polynomial which is basically the remainder, has the smallest possible maximum norm in the interval minus 1 to 1. So, basically I am minimizing the error, in the maximum norm if I make sure that my grid points are located at the zeros of the next higher order Chebyshev polynomial. Is that clear? That is why Chebyshev polynomials are so important, and that is why their zeros give the optimum location of the grid points. They give me the where I should locate the grid points in order to minimize my error term, in order to have the smallest possible error in the maximum norm. Is that clear? So, we will stop here and we will continue with some further discussion on Chebyshev polynomials, which will wind up, and then we will talk about orthogonal polynomials in general. Thank you.